Okay, here's an example that looks at three charges and determines the force on each charge using the vector form of Coulomb's law. The one thing, well, I recorded a lot of this and found out I made a mistake, as well as just having the sign wrong in my original equation, so I'm re-recording this. Hopefully I've gotten it correct. But let's just explain the problem. So we've got three charges, charge 1, charge 2, charge 3, located at these points in this grid. The units is 1 unit, 1 meter from the origin to here. So each one of these tick marks, grid marks, is 0.1 meters. So for example, the position of charge 3 is 1, 2, 3, 4, 5, 0.5 plus 0.2. So x is plus 0.5, y is plus 0.2. And this one is 1, 2, 3, 4, negative 4, negative 0.4, positive 0.6. And so I've got those done later here somewhere. So these are the coordinates of the three charges. These are the three charge values. So we got two negative charges and a positive charge. They're microcoulombs. So it's negative 2 microcoulombs, or negative 2 times 10 to the minus 6 coulombs. So those are the charges. What we're doing here is we have these position vectors, which go from, say, going from object 1, charge 1 to charge 2. The vector starts here and goes to there. So you're going to have negative x and negative y for this. And the first subscript is where the vector starts, and the second subscript is where the vector ends. And to calculate what those vectors are, you just take the position. So let's say vector 1, 3, which is from 1 to 3, is x3 minus x1, comma y3 minus y1. So if you plug in the coordinates that we've specified, you find out vector 1, 3 is 0.9, negative 0.4. So you go 0.9, negative 0.4. You can do the same thing for vector 1, 2, which is going to be negative 0.2, negative 1.1. And then finally, vector 2, 3. So that's from 2 to 3. So this, I'm showing 3, 2 here, but 2, 3 goes this way. So it goes from here to there. So you have plus 1.1, plus 0.7. And the other thing is that the vectors, the other vectors, say R31 is just negative R13. I think I showed that somewhere along here. I don't know where, but I do. Yeah, right here. So the vector from 1 to 3 is negative the vector from 3 to 1, and so forth for the other two cases. Okay. Now, so here are all the 6 vectors, these pairs. One goes one way, one goes the other way. We also need the magnitude of these vectors, which the magnitudes are going to be the same because the values are the same. The sign's different, but you're going to take this squared plus that squared, take the square root, and you get that number. So that's the magnitude. Two magnitudes are the same. The directions are different. And you can do that for these other two vectors as well. So those are the distances between the charges. Now, this is the vector form of Coulomb's law. It says the force on object A due to object B, or charge A due to charge B, is equal to K times Q sub A times Q sub B. So these are the actual charges, which can take on plus or minus values. You divide by the magnitude of the vector RAB. So I guess this should be a little vector here. So we've done that over here. So if A is 1 and B is 3, then you're going to get 0.985 squared. And then you have this unit vector part. Now what I've done is you have to change the direction here. So for finding force on object A due to object B, you have to take the vector from B to A, not from A to B. That's where I got my sign here wrong. And then you divide by the magnitude of this vector. So what I do is I combine these two to get cubed, the magnitude cubed. And this is a vector, and these are scalars. So if you look at the force on charge 1 due to charge 3, it's Coulomb's constant times charge 1, which is, let's make sure I got this right. So charge 1 is -2 microcoulombs. Charge 3 is -4 microcoulombs. The distance R13 is 0.985 meters. You cube that. So if you multiply these four numbers together, you get 0.0753. Now here I use R31, not R13. So R31 is negative R. We calculated R13, but what we need is R31. So this is negative 0.9 plus 0.4. So we just bring that down. We do the scalars first here. So multiply those four together, and then you can multiply the scalar times the components in the vector. So this times that gives you that, and this times that gives you that. And you'll notice the signs. So the force on charge 1 due to charge 3 has a negative x component and a positive y component. So this should have a force. This F13 should be that direction. So let's just go back and look at it qualitatively. So here's force 1, here's charge 1, here's charge 3. They have the same sign, so it's going to be a repulsive force. So F13 goes that way. This is F13 vector, and F31 is going to go this way, and it's going to be the same size but opposite direction. So that's A31. And if we go back to our result from this first calculation, you can see, as I said, the vector should be going to the left and up, which it does, and this one should be going to the right and down, which it does. Okay, so that means that's how we check the signs to make sure we had the original equation correct. Okay, so we've got two forces as vectors, and you can do the same thing for F12. It's Q1 is negative, Q2 is positive. The R21 vector is 0.2 comma 1.1. The distance is 1.118 meters. So if you multiply those four numbers together, you get negative 0.0384, and then you multiply that by each component. So this times that gives you that, this times that gives you that. So that result there, this is F12 vector, and as a consequence, F21 is the vector positive 0.00768 newtons and positive 0.0422 newtons. Okay, and then finally we have F23. That's the force on charge 2 due to charge 3 is equal to K Q2 Q3 divided by R23 magnitude of that vector cubed times R32. I mean, I could have had this 32. It doesn't really matter. The order of those doesn't matter because we're taking the magnitude anyway. The key thing here is this vector has to be the opposite subscripts that you have here. So we have 8.99 times 10 to the 9th coulombs meters squared per coulomb squared. Q2, we'll go over here and find out what those are. So Q2 is positive 3.0 times 10 to the minus 6 coulombs. Q3 is negative 4.0 times 10 to the minus 6 coulombs. The vector, I'll get in just a second. So we go back one page. So we're looking for 2, 3. 3, 2. So that's going to be negative 1.1 comma plus 0.7. And we divide by the magnitude of R23, which is 1.304 meters cubed. So now we multiply those first things to get all the scalars together. And I get negative 0.0487. Just double checking here. And the negative comes from here. And then we multiply that scalar times the components of the vector. So what we'll get is positive 0.0535 comma negative. So that's negative 0.0375. And that's the force vector 2, 3. And so force vector 3, 2 is equal to negative 0.0535 newtons. Units, newtons, newtons. And this is positive 0.0375 newtons. So let's just double check the direction of those before we go any further. So F23 is negative, positive. So it goes this way. Actually, it's a little bit flatter because this is bigger than that as far as the magnitude is concerned. So it's going to look something like that. So that's F32. Okay, so let's go to the picture and see if that's what we would expect. So here we have opposite signs. So if we wanted to draw these vectors, they're going to go this way. So they're going to be attracted to each other. Already starting to be a little concerned here. Okay, so this one would be F23. This would be F32. So that's to the left and down. So let's see where I went wrong there. Somewhere where I wrote something down wrong. Oh, it's right here. You're probably saying, you forgot that. Sorry. So this is negative. So this is negative. So this is positive. This is positive. So it says F32 actually is this direction. And so, and let's go down and fix this while we're, make sure we don't forget to do that. Okay, so that's negative. These are both positive, that's negative. So F32 is negative, negative. Okay, let's go back over here. So F32 is negative, negative. F23 is positive, positive. Okay, so that's good. Let's go ahead and check the last one. That's the interaction between these two. So they're opposite charges. So they're going to be attractive. So it's going to go that way. This one's going to go that way. And this one is F21 and this is F12. So F12 should have both negatives. let's go over here. F12, they're both negatives. F21, both positives. Okay, so that all makes sense. Okay, so the last part is we need to find the vectors F1, F2, and F3, and we do that by adding the two component vectors together, F12 and F13. Force on charge 1 due to charge 2, force on charge 1 due to charge 3. And so I'm recording this for the second time because I found a mistake that I made doing it by hand. I ultimately made up a spreadsheet that did all these calculations, so when I make up a problem for you, it should be easy for me to redo the calculations without a chance of error. But the point is, you've got to be really careful with all these calculations. So just probably what I'll do is I'll let you ask me what the solution is, and then I'll tell you if you did it right, so you can go back and double check your results. But it is very ripe for errors. I think one thing I changed, I think this number here is slightly different than, let's double check our numbers here. So what I'm using here, so F13 is, that corresponds to that, so that's correct. Let's look at F23. It's down at the bottom here. See if I made any changes. You might just check to see if I've made changes here. I think I got everything correctly done. And then we need an F21, I think, this one here. So let's double check on that. Yeah, you can see this a slight difference, 0.00768. I think when my spreadsheet did it, I got 0.00772. So you'll see a slight discrepancy there. Likewise here, you get 0.422. I think the spreadsheet said it was 0.0425. So if you worked along with me, you might have seen where I might have rounded something off. Anyway, these are the values that I ended up using. So all I had to do was take the vectors that I calculated in the previous one and add them together. So this is F12, this is F13. You add the x components, you add the y components, you get to that. For force 2, force on charge 2 due to charge 1, force on charge 2 due to charge 3. Those are the vectors. Add the components together, and then do the same thing for the force on charge 3 due to charge 1 and the force on charge 3 due to charge 2. So you add those together and you get the final result. And I'm just going to show you the spreadsheet just for your interest here. So I'm going to have to pull this over into the view. Make sure this thing is highlighting the here the little corners. Just want to make sure you're seeing this. So what I've done is I've set it up so I input the x and y coordinates of the charges in meters. I put in the charge values in microcoulombs. Then I calculate the vectors R12, R21, R13, R31. So these are the x components of the vectors, the y components of the vectors. This is the magnitude. This squared plus this squared, take the square root. So that's the magnitude, and then I calculate the different forces. Force on charge 1 due to charge 2. So that's using Coulomb's law. You have the x component and the y component. F21 is a negative F12, so you can see these are the same except the signs are different. So this is where I actually do the Coulomb's law calculation. You can see it right there. This one I just say it's negative the other one. So these three here, these 6 are using Coulomb's law, and then these are just the negatives. And then to get the actual final answer, then I add the components together just like I did. So that gives me the final answer in terms of the force values, the x component and the y component. So this would be f sub x and f sub y. And I could also then square these, add them together, take the square root, I get the magnitude of f1 and f2, and then I could also use the inverse tangent stuff to calculate the direction, but I'm not going to worry about that right now.